We'll now talk about unification models for active galactic nuclei. They unify a lot of the observed phenomenology in what's somewhat simpler picture of what's going on. The basic idea is that the structure of the active nucleus is as follows. There is, of course, the big black hole in the middle that provides binding energy. There is an accretion disk of material that falls in, from which a lot of continuum luminosity will come from. The ultraviolet radiation from the accretion disk will ionize the gas clouds near the black hole, the broad emission line clouds, which are close to it and moving fast, and then the narrow emission line clouds, which are a little further away. But somewhere in the plane of the accretion disk, or close to it, there should be a torus of dust, or maybe a warped disk, which obscures the central engine itself from the equatorial plane, more or less. And thus, if you look perpendicular to it, you will see right into the central engine, and you'll see the broad line clouds, the continuum source. But if you look from the side, you may only see the narrow emission line region, because it's much bigger physically than the other two, and it's only partly hidden by the dust. This picture explains a remarkable number of observations. And in this regard, if you look closer to the axis of the system, you'll see broad lines and continuums. So those will be Seyfert type 1 or traditional quasars, or broad emission line galaxies. If you look more from the torus side, you'll see the Seyfert 2s, or narrow emission line objects, or narrow emission line radio galaxies. So at some level, this is almost certainly correct in a broad brush sense. There could be, however, some genuine differences even at any given orientation, and that's subject of some research today, but the big picture seems to be pretty much in place. So let's look at this in a little more detail. Probably the most secure unification is for the Seyfert galaxies themselves. Recall that Seyfert 1s are those where you see the bright continuum and broad emission lines. Seyfert 2s, you only see the narrow emission lines. So look at the picture like this. If you look from the side, you will only see the narrow emission line clouds. The broad line region will be hidden, the continuum will be hidden. But the light from the continuum and broad emission lines will be scattered from free electrons or dust clouds above or below the accretion disk. And some of that will be scattered in the direction of the torus. That is, if we're looking from the side, we'll still see some of that scattered light. And so that opens the possibility of detecting the hidden emission from reflected radiation. But how can we tell? The key feature here is that reflected radiation will be polarized. And if you take spectrum of a Seyfert 2 galaxy, but using polarization filter, you will see that in polarized light, broad emission lines make an appearance. So that's the reflected broad emission line light from electrons and or dust. This directly pretty much shows that the unification picture is largely correct, at least for Seyfert galaxies, but by extension, it will also apply to more luminous active nuclei, like quasars. It took a little while to discover type 2 quasars, but we do have them now. Here is the same case of nearby Seyfert galaxy NGC 1068. The picture on the right shows polarization vectors superposed on Hubble Space Telescope image. One can take images through polarizing filters, and by rotating them find the orientation of polarization, and their length is the relative fraction of polarized light compared to the total. And you can see that there is very nice systematic behavior of light polarized orthogonal to what looks like the principal axis of the system. In addition to polarization, we should be able to see dual cones of ionized gas. The gas along the torus plane will be shielded from ionizing radiation from accretion disk, but the gas in the opening angles will see it and will become more ionized. And indeed, Hubble Space Telescope images of some of the nearby Seyfert galaxies show ionization cones of ionized gas, just like this picture predicts. Here is a more detailed portrait of the Seyfert galaxy NGC 1068, which shows the ionization cones as well as the radio observation. So there is a radio jet that goes in the same direction as the opening angle of the obscuring torus. And so in the simplest sense, the AGN unification scheme works as follows. The obscured active nuclei Seyfert 2s or type 2 quasars or narrow-line radio galaxies. The unobscured one are Seyfert type 1s, regular quasars, or whether or not they're radio loud. And blazars are a special type where you look straight down the radio jet, and that creates a lot of the observed phenomena. There are, however, some very low luminosity active nuclei where there is no obscuration, and yet there is no broad emission line region. So there, more complex things are going on, and there are theoretical models that explain those. One big question is, why are some of them radio loud and others are not? And the explanation almost certainly has to do with the spin of the black hole. And the basic picture is that the rotating ones have preferred axis, which can serve as axis along which magnetic field is wound, from which radio jet can emerge. So the radio louds would have a relatively low spin parameter. It's defined here in the lower right corner. We'll talk a little more about this in the next module. And the radio quiet ones have a spin that's much less than unity that's required for a highly rotating black hole. This does explain a lot of observed phenomena, but then the question is also, how did black holes actually acquire angular momentum? And that's not as simple as it seems, because the material that gets accreted, that causes black holes to grow, has to be at almost radial orbits. Otherwise, it will simply miss the black hole, be in some elliptical orbit, and never get in. So most of the material has to fall right on a radial orbit, because black hole is such a small target, and therefore it will have no angular momentum to speak of. So black holes cannot acquire much, if any, angular momentum through accretion. So then how did they get it? Well, one possibility is mergers of black holes, and we think that that does happen through hierarchical structure formation. And then two black holes would orbit each other. Eventually they would merge because of the loss of energy through gravitational waves. But their orbital angular momentum would then be absorbed by the resulting black hole, and that one would be spinning in the same direction as the two were going around each other. Next, we will address the question of how does the energy really gets generated and how does it get out.